Welcome to a video lecture on Faraday and Lenz's laws. They kind of go hand in hand. This will cover sections 22.4 and 22.5 in your textbook. Please follow along the reading there, and let's begin. Faraday, as we already talked about, first thought that a magnetic field or a constant magnetic field produced a current. Through his experiments, he later found out that it was when you turned the magnet or turned an electromagnet on or off, that's when you actually produced a current within a wire. So a changing magnetic field, or the changing amount of flux, if you change the magnetic flux, so the magnetic field through some area over some period of time, you get a induced EMF, which creates a current. As we'll see in a second, the time matters. So the time, if you do it over a short period of time, you have a greater EMF. If you do it over a longer period of time, you have a smaller EMF, and how strong the magnetic field is. So this is how we relate the EMF produced to the strength of the magnetic field. It's the change in magnetic flux over some period of time. Here's kind of the simple, or I don't know whether this is really practical in a real life sense, but we have a light bulb. It's connected to two wires and another bar or that makes a circuit. In this case, there's no power source. But when you create a magnetic field around this, in this loop here, and you move the bar down, you're changing the area. So this change in area, this is changing the amount of flux. So that change in flux, and it depends on how fast you move the bar, the speed that you move that down, that's going to create an EMF within that wire, that circuit there, which is then going to create a current and thus lighting the light bulb. So here we have our full formula when we write it out. EMF is measured in volts. This is equal to the EMF produced is equal to the negative, and we'll talk about the negative. It comes from Lenz's law. We'll talk about that in a second. N is the number of loops in a wire. Delta phi is that's capital Phi, is the change in magnetic flux. So between 2 points in time, and delta T is the change in time. So in calculating the magnetic flux, it's really just calculating the magnetic flux between two different positions, really, and finding the change in that value. So there's a lot of different ways you can change the magnetic flux through some loop of wire. You can change the area by actually physically changing the loop and making it so it's a larger area, smaller area, something like that. You can squish it, stretch it, and as we'll see in a second, you can turn it also. You can also change the actual magnetic field. You can increase the magnetic field. So there are multiple different ways that you can change the magnetic flux. And we really are only going to be concerned with the initial magnetic flux and the final magnetic flux. Because remember, change in magnetic flux is really equal to the final minus the initial. So we already know how to calculate change. We already know how to calculate magnetic flux. Faraday's law should be pretty straightforward. The second way, and probably the most common way that we'll see the magnetic flux changing, is through twisting or spinning a loop of wire within a magnetic field. So it goes from having maximum magnetic field in the diagram on the left to minimum or zero magnetic field passing through the loop. So in this case, the loop is aligned parallel with the magnetic field lines, so there's no magnetic field going through the loop. So we go from a maximum of some value to a value of zero magnetic flux in the picture on the right. But spinning a loop through a magnetic field is probably the most common one we'll see, or something moving perpendicular into and out, and therefore out of a magnetic field, as we'll show you in a second in Lenz's law. Lenz's law is what gives us that negative in front of the equation for Faraday's law. He reasoned that the magnetic field produced, or the direction of the current produced within a wire, that magnetic field opposes the change in magnetic flux. So in this case, as you move the magnet towards this loop of wire, the magnetic field is increasing, and the magnetic field is increasing towards the wire. So therefore, the loop will want to produce a magnetic field that will oppose that increase. And since it's opposing that increase, the current is going to be moving, as we see here, counterclockwise throughout the loop if we're looking at it from kind of twisting it in our way there. So it goes from B to A in that direction. So current going that way, induced current. All right, so I'm not going to read the steps on the left here. You can go through and read those and write those down on your own. But let's look at this example of a ring. You can follow along. This is in your book also if the picture is not very clear. But here we have a ring. It's there in position number 1. There's no magnetic field moving through it, so there's no current created. Position number 2. Now, the magnetic field is increasing because if there was 0 before, the magnetic field is increasing. The magnetic field is increasing into the page, so therefore the magnetic field produced by the current in the wire needs to be coming out of the page. And if we use our right-hand rule number 2, that's the curled fingers with the thumb along the line. So you curl your fingers out of the page. Current is going around in a circle in a counterclockwise way. Now, once the whole loop or ring is within the magnetic field, there's going to be no current produced because the magnetic field and the area are not changing. And remember, it's the change in magnetic flux, which depends on the magnetic field and area, that creates an EMF. So throughout the middle part here, there's no current produced. Now, when it's leaving the magnetic field, the amount of the magnetic field is decreasing. The strength is decreasing. The magnetic field, the direction of the magnetic field is still into the page, but since it's decreasing, we want to have a magnetic field produced by our current into the page. It's opposite that change. So the change is actually becoming it's becoming less. So we could say that the flux, the change in flux is coming out of the page. So we want our magnetic field produced to be into the page. So if we use our right-hand rule number 2, we curl our fingers into the page, we get our current going clockwise. This idea here is probably one of the more difficult ones to go through. Really go through and just try a couple examples from the book. They're pretty straightforward and they're good practice. All right, first question for tonight. A square loop of 24 centimeters on each side is initially completely in a 0.665 Tesla magnetic field, with its plane perpendicular to B, the magnetic field. But it is completely removed from the field in 40 milliseconds. So, first part, what is the EMF generated? Second part, if the loop has a resistance of 5.2 ohms, what is the induced current? So in finding the EMF, think about how to find the magnetic flux at time equals 0, and then find the magnetic flux at time equals 40 milliseconds, which if it's completely removed from the field should be pretty easy. From there, you find the change in magnetic flux over the change in time. That gives you the EMF. All right, so there you go. First problem, put it in online. Awesome. Question number 2. A wire loop of radius 0.3 meters lies in so that the external magnetic field of 0.3 Teslas is perpendicular to the loop. The magnetic field reverses its direction and its magnitude changes to 0.2 Teslas in 1.5 seconds. Calculate the magnitude of the average induced EMF in the loop during this time. So once again, same thing as with the previous problem. Calculate the magnetic flux at time equals 0. Magnetic field times the area, and since it's perpendicular, we know that cosine of phi is going to be 0. Cosine of the angle, is going to be 0. Cosine is going to be 1, so that we go through with that. and then calculate the magnetic flux at time equals 1.5 seconds. Change in magnetic flux. Remember, it reverses direction, and it changes a little bit. It changes in magnitude, so you have a whole different thing. And go through that for this part. I will put some stuff up online to help make sure you can check your answers. All right, final question. Question number 3. Determine the direction of the current in each of the loops, 1, 2, 3, 4, 5, in the diagram to the right. Number 1's at the top, number 5's at the bottom. Number 5 is the only one with a different size area. But just keep that in mind. Region 1 has a magnetic field out of the page, while and it's a constant magnetic field, uniform, and region 2 has 0 magnetic field. All loops are moving at the same speed, but their direction is different, so you can find the direction on there based on this chart. Lenz's law, change in magnetic flux. I'll put the answers online so you can check this, all right? Thank you very much. Have a good night. Put your answers into the sheet.